Hi everyone, my name is Sophia Pedigo, and I'm back again with part 2 in a problem in which we're going to have a bar that looks something like this. And essentially what we're trying to do is we're trying to develop a time-varying temperature profile for this bar. So we're going to say that we're working with some time delta t, right? So I don't know, it could be 0. We'll just say 0, right? And this bar is going to be broken up into different little segments here. So this would be like segment 0, 1, 2, 3, etc. Now, what we want to do is, like I said, we're going to create a time-varying profile, and we want to create or derive an equation that gives us that information. So essentially what we're going to be doing is we're going to be using the heat diffusion equation that I looked at in my previous video, and we're going to be rearranging that and ultimately getting an equation that'll give us that we can use to get the temperature profile for varying times. But before we go into that, I want to go over the convention that I'm going to use for, I guess, denoting the time and the position on this bar. So basically, we're going to call this T for temperature, right? And down here, this subscript is going to be J for the position that we're at. So like this first little chunk would, J would be equal to 0. For the second one, J would be equal to 1. And then up here is going to be the time at which this occurs. So in this case, it would be our delta T, which I said was equal to 0. So that would just look something like, if I'm plugging in the subscripts and superscripts, that would look something like the temperature at the temperature of position 1 at time equals to 0, something like that. So that's kind of the convention that we're going to be using and plugging that into the heat diffusion equation to get this time varying temperature profile. So I'm not going to go into the nitty-gritty details of how I derive this equation, but basically we are using that same convention that I just showed you, where you've got the J subscript and the N superscript, and we're going to differentiate this equation using that convention. So when we do that, when we take the derivative of both sides of this equation, this is what we're going to get. We're going to end up with T sub j to the n plus 1 minus T sub j to the n. That's all going to be divided by the time delta t. And then on this side, probably move this over a little bit, we're going to have an alpha, which is the heat diffusion coefficient. I always forget the name of that. So we're going to have alpha, and that's going to be, this is kind of a nasty little thing. I'm going to put brackets so it's kind of easier to see. And this is going to be T to the N J plus 1 minus T to the J, or T sub J to the N power. All of that's going to be divided by delta X, and then we subtract T sub N. Oops, bring that T into J. This one's going to also be divided by delta X, and this whole thing will be divided by delta X. Now, this is kind of a nasty thing, but we're going to rearrange this and move this around so it's a little bit easier to work with. For starters, I'm going to isolate I don't know, what am I